Thank you. I will not talk about Elixir at this Elixir conference, but I want to mention my connection to Elixir. So we'll start by this. Let's see. It doesn't show my image here, my slide. Okay. Will I be able to see my slides here later? Okay. So I started to learn Elixir in 2018 to solve advent of code. And I liked it so much that I continued to do it every year. And I even went back to do all the previous ones. So one time a year I use Elixir and keeping it fresh. Okay, so now over to the real presentation. So this is my personal history with Beam. I'm talking about most of what I've been personally involved with. But we will start back in time in 1980 when I learned to program on a TI-59. It was a programmable calculator. It had about 1 kilobyte of memory. So I learned to write small and efficient programs doing that. I was also involved in a users group that has a newsletter, so I wrote a lot of articles about that, how to program the TI-59 and also how it worked internal and so on. A little bit later, I went on to Texas Instruments home computer. It had very slow BASIC, but I programmed mostly in Forth and assembly language. And there was a newsletter for that one as well. And this will actually become relevant a little bit later. But enough about me for a while. At the CS lab, computer science lab at Elmtel, a project started in 1986 to figure out how to best program telephone exchanges. And it was not the intention to create a new programming language. And of course, that was exactly what happened. They developed a prototype for Erlang in Prolog. It was good for trying out new features, trying out what features the language should have. But it was too slow for real applications. So they went to Joe's abstract machine. So Joe Armstrong wrote the compiler, and Mike Williams implemented the runtime system in C. So JAM was a stack machine. It meant they used a stack for operation, for operands and for passing arguments to functions. So here we look at an example how to evaluate 37 plus 5. So first we need to push the first operand to the stack, 37, like so, and then the 5 to the stack, and then the plus operator will pop those values from the stack and put back the sum, like so. And JAM was about 70 times faster than the Prolog prototype, but it turned out that wasn't fast enough for some applications. So in 1993, Bogomil Hausman, user called Bogdan, invented Turbo Erlang. And it compiled Erlang code to C code. And it was said to be 10 times faster than JAM. So here we will look at an example how it's compiled to that machine. So here's a append function. So here's how it was compiled to C code. So these are all C preprocessor macros that expand to a lot of code. So this early implementation has some drawbacks. So the generator code was much larger than JAM code. It was so large that it made it impractical to use in real systems. There wasn't enough memory left for data and processes. So, and compilation was very slow. Also, the name didn't fly. But Bogdan continued with a new machine or improvement of Turbo Erlang. The next one was called Bogdan's Erlang Abstract Machine, or Beam. The difference here was that one could choose to compile either to C code or to the code for the Beam machine. The idea was that for time-critical code, one could compile to C code, and that would use much more memory. For other modules could be compiled to the code for the Beam virtual machine. So Beam is a stack machine. Sorry, it is a register machine compared to JAM, that was a stack machine. So Beam uses registers. So to do this evaluation, first we have to move 37 to X register 0 and 5 to X register 1. And this instruction will add X0, X1 and put the result into X0. Like so. So here we have the result in X0. Okay, just a warning about simplifications are made to make clear what I'm talking about. The simplification I've already done and some of what is coming. So in 1996, Open Telecom platform was formed. The group was formed and was the name of the platform. So the UTP team had office in the same building as the computer science lab in Elixir on Götalandsvägen. At that time, I was working at the Ericsson, but not with Erlang. But I happened to be working in the same building to the right. And one day when I was going home on the bus, I happened to meet Tony Rågvall. And he had written some articles in the newsletter for the home computer. So he persuaded me to start working with Erlang, to help develop Erlang. And so I did. I started working at UTP at the end of 1996. I started working with Beam in 1997. So before I go on, let's talk about the meaning of Beam today. Today, Beam is usually meant the entire runtime system. So not only the code loader and thread interpreter or JIT, but also the scheduler, garbage collector, all built-in functions, drivers, and so on and so on. At that time, Beam meant just the loader and thread interpreter part of it, and the runtime. The source of the runtime system was shared with JAM. So keep that in mind when we talk. I have done a lot of changes to this small part of the runtime system. So at that time, both runtime systems were still maintained, and then that was because it was difficult to keep both of the systems working. They had some differences. It was particularly easy to write a new BIF for JAM that didn't work properly in Beam. So we long-term goal was to make Beam good enough so that we could retire JAM. And there were some challenges needed to overcome for that. Beam at that time had over 300 instructions, and each instruction needed handwritten code for loading the instruction. And another problem was that the Beam file format was not stable. There was a magic number, version number at the header of each Beam file, and it changed in every release, even minor releases. I will explain why later. But that having a new incompatible Beam file in every release was not practical for real application for customers. So now I will take a closer look at Beam, doing a deep dive into Beam, more about it works. So I was talking about the registers. I shall show some more examples of that. The stack is used for values that need to live longer. The X registers are used for temporary values and for passing arguments to function calls. And the registers, the stack slots are called Y registers. And that continuation pointer is return address to the calling function. So let's look at executing some move instruction. First moving x2 to x1 and x3 to y0, and moving the atom arrow into x2. And there were different move instructions in Beam, depending on operand. So actually, the old Beam looked like this. There was one move XX, move X register to X register, XY to X register to Y register. And in the Beam files, that was translated like this. So there are 2 bytes used for each register operand. But when loaded into memory, this was expanded, and that's why it needed handwritten code. It was expanded for each move instruction, expanded to 3 words, 24 bytes. And the reason for that expansion was that the first word of each instruction contains a pointer to the executable code to execute that instruction. So that made Beam fast, very efficient instruction execution. And this double ampersand is an extension in the GCC. C compiler labels as values, allow you to take address of a label and then later do an indirect jump to that label. So when I started working with Beam, I decided this handwritten loader code had to go. So I had to think of something to eliminate all that code, because it was a maintenance nightmare. So I decided to write a script in Perl to have some input file and generate code for the loader, and also for the compiler, and also for loader and runtime system. So it's called the Beam makeup script. It's still used to this day, but it's become more complicated. But yeah, so the first input file is genop.tab, and it simply gives the number of each instruction. So here is a number for the move instruction. And yeah, I decided that the compiler should only have one move instruction. So instead of having this in the old Beam, one move instruction and moving the types of the operands to the operands themselves. And then there was another complaint. There was a complaint about Beam at that time that the Beam files were much larger than JAM files. So I decided to do something about that as well. So I implemented a new efficient encoding for operands. So here is example how to encode X register 2. So first type X register is type 3, and that goes into the 3 least significant bits. And the register number itself goes into the most significant bit. So this is packed into 1 byte like this. But then for the runtime system, still want to have the same instructions, a different variant for different operands for efficiency. So here is defined the legal variants of the move instructions. So move x, move x register, x register. The last one is move c, x. It means move a constant, which is an integer or an atom, to x register. So, and then also another file could define the implementation as a template, and then the script would expand that for each variant of move instruction. So it's move x, y, it's moving x register to y register. I will show you the complete code later. So with having this script, the same instruction would result in the loaded code as before. But now having the script, I could implement some new optimization that would have been hard to do before. For example, if you look at this, each move instruction takes up 3 words, and the register number having 4 bytes to 1 word for register number is wasteful. So they could actually be packed into 1 word, and the beam makeup script would take care of all the boring details to do that, both to pack them and to unpack them later. So having this same template, here is the complete code to unpack it, using shift instruction and the bitwise end. And this is also faster because it read less data from memory. There was another optimization was present in the old beam to combine beam instructions. Frequent combinations of beam instructions could be combined. So the compiler did this in the old beam. I removed that optimization from the compiler. Instead, I introduced something called what's called transformation rules in the beam loader. So a rule like this could match a sequence of 2 instructions and combine them to 1 instruction. So here is an example. They have the instruction sequence in the middle and then the pattern at the top. So we see the pattern will match the first operand. The first operand is either a constant or a register. So that matches. And the second instruction also matches. So then the loader removes the previous instructions and replaces it with this one. And having made the script do this, it was easy to add that for other common combinations that were not done in the old beam. In the old beam, it would have been much more work to do these optimizations, and you wouldn't know whether it was worth it before you have implemented all of it. So, for example, what here two move instructions could be combined. So the other challenge I mentioned was the unstable beam file format, and the main reason for that was that the compiler knew too much. It had to know about all BIFs in the runtime system because different instructions were emitted depending on whether it was a call to a Erlang function or to a BIF. So this was encoded with index into a table of BIFs. So yeah, the compiler and runtime system had to stay in sync. So I I changed the calling convention for beef to be the same. And then I added a little small optimization using a transformation rule to translate for here, a call to beef here would be replaced with a call beef 0 instruction. So this is a summary of what I've talked about so far. So I made the beam makeup script to simplify maintenance and to make it easy to add more optimizations. And I was able to optimize so that generating C code was no longer necessary. It didn't give much of the advantages longer, so we could remove that support. That was also difficult to support. And in OTP-R5, the beam file format becomes stable. The same beam file format is used today. And we removed support for JAM in OTP-R6. So now we'll talk about an optimization that I added in OTP-R12. It's called stack trimming, so I will show you why that is a good optimization. We'll also dive a little deeper. We'll actually look at the garbage collection a little bit later in this. But so here's the map function, and it can be called like this to produce negative. Each integer is replaced with minus, so that the negative version of that integer. So the main point I was showing here is the number of wide registers used here on the stack. In case it's difficult to follow this example, so here I show how we evaluate map/2 without stack trimming. So the arguments are in the X registers 0 and 1. And when entering function, everything that will be destroyed, the code actually need to be saved to the stack. So that is done. If the closure or fund, as we call it in Erlang, will be saved on the stack. And then the closure will be called, returning -1. Let's see. Yeah, and then we'll store that on the stack and do a recursive call on function. So then it will continue like so, and when it reaches the end, it will start returning and building the list in reverse. So here we have the result. So as you can see here, the remainder of the list was stored on the stack, but never actually used later. So it was stored temporarily to save it, but then it was not used. And the problem with that, if there would be a garbage collection, it would be copied. So now I will actually show a garbage collection here. How it's done. So we have something called a heap that list elements are stored on, and tuples also. So we have tagged pointers to the heap, L:148, points to that address on the heap, and the tag pointer is that we put tag in the two listening bits. They are always normally 0 because all those addresses are aligned at 4 byte aligned. So we can use those bits to indicate that this points to list element, and the other tags for other purposes. So now we can start doing the garbage collection. The garbage collection will go through the stack and X registers. For now, let's assume there are no live X registers. So it will go through the stack, look at this L:148. Okay. So before we can do that, we need to allocate a new fresh heap to where to copy it. But now it sees this address, copies to the fresh heap, and it also stores a forwarding address, that moved there in red is a forwarding address to where the new value is. Okay, and then it's the next list element on stack is copied. So now we have everything on stack there has been copied. But now we'll go through the fresh heap, see if it points to anything on the old heap. And here it sees the moved word, the forwarding address. So it can copy that. So we'll take that, replace that pointer. And now everything is copied to the new fresh heap. So we see we have all pointers in place. Same result, same terms as before. And now we can remove the old heap. So that was a garbage collection and unnecessary in this case. So what I added here was stack trimming to trim the stack. So we'll show that. So here, when we're doing the recursive call, we'll do a stack trimming. Here I'm zoom in on some beam code. So we want to keep the -1. So we will move it upbound to Y1, and then trim the stack with one element, and then we can do the recursive call. So now we only save on the stack what you actually need, and that will improve performance. And now unwinding. And another thing, the stack and heap grows towards each other. So a nice thing here is that when we remove things from stack, the heap grows. So there can never be a garbage collection during this when we are unwinding the stack. Yeah, that optimization. Now let's move forward to OTP 24 when we introduce the just-in-time compiler. And there had been 2 previous attempts to do a just-in-time compiler, and they didn't actually improve the performance, so they were abandoned. But Lukas Backström and John Högberg wanted to try another way to do it. Actually, a simpler way actually is to translate all code that's loaded to native, because the previous attempt was to just translate hot code to native code, but I think let's try to see if we translate everything to native code. In that case, we will not have a problem switching between native code and interpreter code. We don't need the usual Beam interpreter at all. So that would be vastly simpler. So the loader was changed to just translate it. So here, move instructions for the same Beam code is translated to native code, 16 bytes. And the same kind of optimizations could be used in the loader to, for example, combine instructions. So here, 2 move instructions are combined to one instruction. So, for example, you have this instruction. So we are moving 2 Y registers that are next to each other to X registers are next to each other. And that can be optimized using SIMD instructions, so that can read 2 words from memory at once and then swap them and write them back. So this results in a smaller, shorter instruction than the previous one that was 16 bytes. So okay, here's another example. In OTP25, we started to let the compiler help the JIT. So to explain this, so here we have a simple function calling using the plus operator, and this results in the following beam code. And this is expanded to quite a lot of native code here. And why is that so much? It's very simple to add 2 integers, isn't it? But there could be other things than integers. There could be floating point numbers. There could be a big integer that doesn't fit in a word. Or there could be an error. You could try to add something to an atom. So all of that has to be handled by the JIT. But if the compiler can tell the JIT that it's not necessary, it can be simplified. So here, if you use another version of this function that does a range check, so ensure that the I variable must be in the from 0 to 1023. Then the compiler will emit type information. So if we see, let's see, do I have a pointer? So here is a type. This TR means a register. Here's a register, and here's the type. So it says it's integer in this range. So the compiler started to emit this information. And with this information in place, so here we have a previous code, long code. We can remove a lot of instructions here. It will leave four instructions doing actual addition, and then actually that can be reduced to 3 because we can be a little bit smarter on registers here. So this might make it much nice, smaller and faster if there are types, known types here. So yeah, personally I come full circle. I'm starting in 1980s to write articles about programming with the TF-59 and deep diving into that, examine its firmware and so on. And now recently I started to write a blog post about the Erlang compiler, the JIT and the beam and so on. So if you're interested, there is the Erlang blog. It's the first link. So there are blog posts by me and other people in the OTP team. Also, if you're interested in beam makeup script, that is also available as internal documentation for Elixir application. So yeah, so I think that is all. Thank you all for listening.
Thank you, Bjorn. So first question we have is, were the optimizations applied to Beam already standard in other projects during that time? Or were the techniques invented by you and the team?
I think that I've invented them, but you mean for interpreted languages or yeah, I suppose it doesn't say that, but yeah, I didn't find the ideas, so I think as far as I know, it was my own ideas. Yeah.
We have another question. What are the next steps for the Beam?
From now on, yeah, we are talking about the Beam 2. Not sure when it will be, but there is a little bit difficult for JIT to generate very good native code. So we were thinking about introducing a new Beam format to make it easy for the JIT to do its own Redist allocation. And that would result in more performant code. But that is just an idea for now, so it could be 5 or 10 years. But we have been thinking about that. I think we would need to do a new Beam format for that, the package the Beam instruction in another way, and also think how to handle backward compatibility. We still want to be able to use small embedded systems, nerves and so on. Yeah.
Great, I think we've got time for one more question. If the Beam was written new today, what would be different?
Today, I have no idea. My experience is from building the Beam in this way, so I'm not sure. It is very circular reference. No idea.